So welcome to the University of Maine's Artificial Intelligence webinar series. Today's panel is focused on AI for agriculture. Before we start, I'd like to thank the University of Maine's Office of the Vice President for Research for planning this event, and IEEE Maine Communication and Computer Society's joint chapter for sponsoring this webinar. Before we begin, I want to remind those of you attending to use the Q&A feature to post your questions. All of these questions will be asked after each of the speakers, or after all of the speakers have completed their presentations. So again, thank you for joining us, and it is now my great pleasure to introduce our first panelists. Today we have joining us Dr. Stephen J. Thomson. He is the National Program Leader with the USDA National Institute for Food and Agriculture. He engages universities, other federal agencies, and industry to provide national leadership in capacity and competitive grant programs. So with that, I'd like to introduce Steve. Thank you.
Yes, I'm Stephen Thomson with USDA NIFA. I've been with NIFA about a little over 5 years now, and I'm the national program leader in the Agricultural Systems Division. I'm an engineer by training. In my background, I was on faculty in 2 different departments at Virginia Tech, and I was with USDA ARS before I came here. So I was associate professor at Virginia Tech in the 90s. So anyway, so let me give you a quick update first on some changes that have been made. The new Secretary of Agriculture, Tom Vilsack, he's been here before. He served under President Obama, and we expect continuing interest in some of the initiatives that are already there. Rural broadband, precision ag. He was a big proponent of robotics in agriculture, and climate smart agriculture will be more pronounced in this administration. Dr. Carrie Castile, she was a science advisor to the commissioner for the Louisiana Department of Agriculture and Forestry. And she has an extensive extension background. So I'll give you a short outline. This first part of the presentation will not take very long. I'm just going to emphasize a couple of aspects in plant agriculture and an example for precision livestock farming. And then I will get into the stuff you really want to see. The research programs that involve most of the research programs and the technical side of things that involve AI at USDA NIFA. I'm not going to talk about the educational programs, but there are some that you can actually see those in the online on the NIFA website. Time won't allow me to get into the weeds on every program. And then some future outlook. So I want to center on one aspect of AI, cyber physical systems, which basically is a pretty broad term, is where physical and software components are deeply intertwined, and they operate at different spatial and temporal scales. And so, you know, many times you'll have a system with sensing, interpretive, shall I say, adaptive control, data analytics in the middle part, and then an output control or decision. And there are feedback loops involved. You may have modeling in working in concert with sensing and these kinds of things. You know, some of the obstacles for, I would say, tech adoption and CPS. And the reason I say this is because that middle part is so important. You know, you have the sensing, but then the interpretation, how ultimately how the farm manager is going to be able to use this is extremely important. There's some issues on the perceived relevance of the technologies. Actually, just awareness of the available technologies has been a problem. Farmers like to fix things, so simplicity, user's guides. This is not only good for the farmer, but for any consultant that is working with the farmer. And there's been an issue with trust in tech and DSS, decision support recommendations. Now, one of our speakers later is going to talk about the adoption side and you know, in a lot. Yeah, I think he has a very creative, he's going to talk about a very creative solution to this kind of, or shall I say, towards a solution to this kind of thing. So I will not talk too much about the adoption area. Now, when you're talking about plant-based management, you know, there are a lot of sensors out there, and they could be ground sensors, aerial sensors, various things. And there are varying opinions on which sensing systems work better to detect certain anomalies in the field, okay? But that research is progressing and has progressed well. Like I said before, the middle part of it, the interpretive part is the kicker right there. Let me give you a very short history on the precision ag side of things. Back in the mid-'80s, people were starting to realize that, you know, you could have a setup where you're applying inputs only to where they are needed. Okay, and an article from 1985 that you won't find. I have a printed copy, but I could not find it anywhere else. Farming by the Foot: Proposed Use of Lawrence C technologies, which, you know, the accuracy is not nearly as good as GPS, but this was a concept in the early 80s. John Schuler at the University of Florida developed a combine yield map in 1986. I think this was manually obtained data. So this gives you an idea where when these concepts were first thought about. Some work from my own background. This was about a little over 20 years ago. We thought, hey, you know, let's just take a high-res video camera and put it in a crop duster. So anyway, we got an image like this, and we were able to separate out grass weeds from broadleaf weeds and cotton, just as a conceptual idea for future use in targeted spraying, for example. This is graduated to much more sophisticated systems. Up on the top left is a push broom hyperspectral scanner on UAS. These scanners have decreased in size. The one on the top right is a hyperspectral scanner that is a frame-based system. These companies in Finland, there are some companies in Finland that have developed these frame-based systems, which would be easier to use. But I don't have any experience with them, so I'd be very interested to know. One on the bottom is called a Red Edge multispectral imaging system by a company called MicroSense. And so they're basically filters in certain ranges of the optical spectrum, including near infrared also. And I alluded to this before, but cyber-physical systems can be the bridge, in my opinion. I think these will work better if you have sensing, if you have sensing and modeling or sensor fusion. Sensing and modeling and synergy. I mentioned that the data analytics part is very important to get that right. DSS tools, decision support tools, are becoming readily available for some applications, but not others. I've actually funded a couple of grants for irrigation, for example, where one is coming out, trying to reduce all these decisions into a usable app for the farmer. So we'll see how that goes. Now, I just want to point out the bottom part here. We're talking about data interpretation and adoption. I would say, now this is a slide dealing with variable rate technologies, but this can apply to many different aspects. say that low adoption on inputs that require more data analysis or prescription algorithm development. And this has been the case. This is part of a slide from a study on adoption from Purdue University. So I want to give one example, irrigation example. Look at the yellow, no, not the blue and green bars there. The adoption of technologies for irrigation has been really, really poor, very poor. So let's conceptualize something. You may have some, this is not really a flow chart, but there is flow here. You may have sensors in the field. You may have a model of water balance that also depends on root distribution and root water uptake in different zones. So in a nutshell, what this one is doing is using sensing and modeling in synergy to make better estimates of crop water use. Okay, so this is a cyber physical system in a way. Let's not forget technology for small farms. Now, this is something I was involved with. You can't get any simpler than this. This is a wash tub with a toilet float and 2 marks on a back plate. The black mark would say field capacity. That means well-watered conditions. The red line would say irrigate. Okay. The trick is calibrating this to the crop soil combination. And in my study, I also used soil water sensors in synergy with this. So, so we did publish something on use of this evaporation pan. And then in the future, what you would do is try to translate this into something. You might actually take a signal from this wash tub and send it remotely or something if you wanted to do that. This is a very simple concept, and not just for small farms. It can be used for larger farms also. Farmers like simple, okay? But there's a lot more to calibrating this than meets the eye. Microsoft has actually gotten into the game too, where they are essentially replacing expensive ground-placed sensors with cheap Wi-Fi receivers at several locations. And the principle here is to measure the relative flight of a signal to infer soil properties. And this is a very good paper at the bottom I would suggest that you get hold of. This is just a proceedings article, but for a proceedings article, the results look very, very promising. Precision livestock farming. What you're doing here is you have to make immediate decisions in real time, whereas plant-based agriculture, you can make decision in near real time and depending on what you're looking at. And many times you're saving the data from year to year. Say, if you have yield maps, you want to know what the yield trends are from year to year, okay? In this case, you have to take, for animal comfort and these kinds of things, many sensing inputs like biosensing, environmental, diagnostics of the systems is a big part of precision livestock farming. That's what PLF stands for. And you have some of the same concepts as you do for plant-based. You'll have sensing, you may have modeling, adaptive learning. And I would also submit that visual monitoring is a big part of this too. You know, I can envision having a large screen with many, many bar graphs so that the farm manager not only, you know, this model-based analysis could be black boxed, but if the farm manager sees the data up on the screen, they may actually look at something, hey, this doesn't look right, you know, and check out what's going on. And this could also be used to update the algorithms in a system like this. So this is just a concept. Okay, if I'm not short on time, I'm going to get through this. I want to mention how NIFA funds are provided. Let's get to the grant side. About 50% of our funding goes to capacity grants, 50% to competitive grants. The capacity would be the Hatch, Evans, Allen, McIntyre, Stennis, and these type. And I would implore people to, when you're sending a project initiation for a capacity grant, really pay attention to the detail on this. As if I see a 3-sentence methods, I'll send it back. So make sure these are fleshed out very nicely. All right, I'm going to go down the list here, and some with more detail than others. The first one is the engineering for agricultural production systems. Now, this is in the AFRI portfolio. The funding amount has gone up to $650K per grant. The funding rate's been rather low, though. I had a 40% increase in the number of proposals from 2019 to 2020. Funding rate's down near 9% with the same amount of money. Data science for ag systems, funding rate's a little bit higher. The 1 million level is for CINs, which is Coordinated Innovation Networks. Okay. National Robotics Initiative is now, for these, you need to look at the NSF website to see the solicitations. However, National Robotics Initiative, Cyber Physical Systems, these are both funded by NIFA, and the panels are run by NSF. NIFA has a say in helping select the panelists on this also. All of the NIFA submissions have been within the real-time agricultural data analytics and control section. Smart and connected communities is also a part of this, and you can see what our NIFA's aspect is on that. Signals in the soil, another one. Jim Dobrowski has $5 million. My contribution is variable according to the budget. A few more pertinent programs, AI Institutes, of course. These are the big ones. We are in the process of reviewing proposals now for the second year of funding. We funded 2 grants for 2020, one from PI from Davis, California, the other, the University of Illinois, and several collaborators, collaborative universities and companies too. We're working on the solicitation for 2022. We will fund at least 1 grant out of that one. SBIR, of course, Plant Production and Protection Engineering Program, is 1 out of 10 programs from our SBIR portfolio. There's a 15% funding rate across the board. If you are registered in SAM, you have to be registered in SAMs and have a DUNS number, or you won't get through the front door. Small and medium farms, there are some pretty interesting technology-based grants funded out of that program also. Now, if you're involved in the adoption or diffusion of agricultural technologies, one of these 3 programs should be considered, especially economics, markets, and trade. Okay, so that one we're actually modifying to enhance these aspects.
So Steve,
yes.
I think we're over a bit. If you want to just put up your final.
Yeah, this is my final slide.
Okay, thank you.
A couple of observations. We need to integrate social sciences even more in our grant programs. And emphasize extension and education more in AI institutes. Anyway, you can read all of this. I'm over time, so we'll talk about it later. Thank you very much. And if you have, if you want to serve on a grant panel, send me a CV. To find grant summaries, look, Google USDA CRIS and use the assisted search. Thank you very much.
Thank you so much. It was very well done. So for our next speaker, I'd like to introduce Dr. Naresh Devineni. He is an associate professor in the Department of Civil Engineering at the City University of New York City College. He holds an MS and PhD in civil engineering from North Carolina State, and he did his postdoctoral studies at Columbia. So with that, thank you, Dr. Devineni.
Great. Thanks, Susan. I'm going to share my screen now. So today, the title for this talk is Role of Big Data Analytics in Securing the Future of Water, Energy, and Food. Really, what I'm trying to present here is the applications of the classical AI techniques like process optimization, predictive models, and how we can use big data to how we can leverage big data and use these classical AI techniques to find solutions for water, food, energy problems that we are seeing a lot these days. So on that, I'm going to present two stories. One is an application in India, and one is an application in the US. Both problems are national at scope. For the case of India, the problem identification is that there is an unsustainable practice, agricultural practice currently going on in India that will lead to an acute water stress. It is already water stress, but it will really lead to much more acute stress if the practices are continuing. So for identifying this problem much more closely, what we did is to use big data from disparate sources. We assimilated all of those things, and we tried to learn about the current water stress using the big data. So we're learning about water stress from the data. And then the solution we propose is then to use data-driven predictive techniques and process optimization. These are like the classical systems methods to remove the stress while still achieving food security in India. So in a way, we're trying to find, can we really solve this problem using AI techniques? In the second application, which is the planning for United States agriculture for climate change, the problem identification is that extreme temperatures under climate change will reduce yields for several of the major US crops. So for that, we try to use a Bayesian learning method to understand and predict crop yields based on technology, based on temperature and water stressors. And the solution we're trying to come up with is use, again, systems optimization methods to predict crop switching strategies to mitigate yield losses. So I'll start with the first story, which is the story of India. And here I'd like to acknowledge my colleagues here, Upmanu Lal from Columbia University and Shama Parveen. Here the question is, based on the current crisis in India, can we solve this issue and make India one of the leading agricultural sustainable producers in the market with an N times boost in the rural income? But really, let's look at the problem first. If you look at this, these two images, one is an image on the left, which is provided by GRACE satellite, which was detecting largest groundwater mining operations in the world. And that region that you see here, which is in red color, is also the place like the football of India. It is heavily populated. And what you're seeing on the right is the actual groundwater extractions, the number of wells that are installed in those places. As you can see, like heavily populated region, heavy groundwater extractions, mainly for the purpose of agriculture. But this problem actually started in the 1950s and 60s when the country went through a big famine and food insecurity because of low yields and high fluctuation, poor storage distribution system. There were market fluctuations, there was stock manipulation. To arrest the trend, what the government has done at that time is to float this idea called a national grain procurement scheme, where there was guaranteed price on select crops, and all these crops used to be procured for the purpose of national food security. So this really initiated the Green Revolution, where you have improved cultivators, better fertilizers and practices. There were research and extension programs created by the government, while at the same time, it was also giving irrigation provisions to buffer climate variability. And one of the biggest additions at that time was to give electricity and water for free, which means that we have heavy groundwater installations. And as a result, we have huge groundwater pumping to sustain the climate variability for agriculture. The figures on the right that you see here is that just to outline that India is one of the highest groundwater extractors compared to a lot of countries in the world. And the figure on the bottom you see here is that although India has other sources of irrigation like canals and tanks, because of their unreliability and because of guaranteed prices and free electricity, the trend of usage of groundwater irrigation has gone up significantly. So it's now one of the predominant agriculture irrigation technologies in India is just extracting groundwater. And as a result, what you can see here is this is the current cropping pattern. A lot of the cropping patterns have shifted from the traditional practices, which used to be there done before the 1950s. Now, because their farmers are reacting to these incentives, what you see here is rice has moved to the northwest countries of states of Punjab and Haryana and Uttar Pradesh. And what used to be pulses and cereals are now completely not grown in that place. But when you look at the climate side of the story, you find that that place where you are actually growing rice currently is a dry land. And this is a place where you only get a third of what is required by rice. But nevertheless, this place contributes to the highest grain production in the country because most of that is coming from the irrigation, which is coming from groundwater. And as a result, you see that while you have food security now, it's coming at a risk of water security for the future of the country. So the first thing we did was to identify what this stress is. So we're trying to use these big data methods to identify the stress, predict the water stress in the country, and look at what are these stressy zones. So for this, what we did was assimilate a large database, 100 years worth of daily climate, rainfall, temperature data. We assimilated all the current cropping data sets from India at the district level. And you can see the dimensionality is really like multiple fold. The data sources can come from various sources, a lot of them from government websites, a good number of them from research articles and just talking to locals and getting those surveys. We used all the data to first predict water stress measure, which is really a function of rainfall, temperature, evaporation, water demands, and crop biophysical characteristics. And what you see here is just an illustration of that water stress. Without going into much detail, what you can see is that if it is in the red zone, it is really bad, both at the annual water stress measure, and even you look at multi-annual, it is also very bad, meaning if this place is susceptible to multiple years of drought, the stress really accumulates and becomes a chronic problem instead of just an annual problem. And when we integrate these two annual and multi-annual stressors, what you'll see here are a development of an agroecological zone. Sort of what we are seeing here is that some places are sustainable, which are the blue zones. Some places are prone to multiple years of stress, multiple years of drought, which are the red zones. And some places are really unsustainable for agriculture, at least based on the current cropping pattern. So the green zones that you see here, which means that you really need shifting of crops from those places. So then if this is the problem, what the solution we're trying to propose is, can we actually use all this big data in a systems method? Process optimization is what it's called in AI language, to predict what the sustainable zones of agricultural enhancement would be. So that way we're trying to address climate, energy, water, food income nexus, all conjunctively in one solution. And the question we started asking was, when we looked at this figure, which is the acreage of rice and pulses in Punjab, the northwest part of India, you can see since the 1970s, there's a huge increase in the cultivation of rice and a huge drop in the cultivation of pulses, which used to be the traditional crops in those places. And much of this rice, as I said, it's not raining so much there, but all that irrigation is coming from groundwater. And, in fact, up to 70 or 80% of that irrigation is really through groundwater. So we started asking this question, can we use some data analytic techniques to solve this? So the question is, did the green revolution really stick in the wrong places? Could India's water stress be reduced just by changing where what is grown? So then can these analytic methods help us identify what those zones are and how much to grow in those places, like a decision tool, and what is the role of climate in these things? So we created this large-scale process optimization model, which is trying to predict sustainable zones for agricultural enhancement. The inputs of this model are the climate scenarios, more than 100 years of climate, precip and temperature at the district level, and the crop eligibility, whether the crop can be grown there or not. We are using all those inputs to predict water stress, which will predict crop yields, which will in turn predict crop production. Then the other inputs are current prices of the crops, cost of cultivation, cost of irrigation. So all those go into this process optimization, and the objective is to maximize the national revenue that is coming from agriculture. While we have a bunch of constraints which are trying to keep the things sustainable, we don't want to increase the land which is currently under agriculture, meaning we are already maxed out on land, so we are not using more land. And we are trying to keep irrigation to a sustainable limit. And we also played around with a scenario where there is no irrigation at all across the country. And you'd be surprised that even without irrigation, you can still get national food security on an average year. So the model runs as a simulation optimization model, and you can develop multiple scenarios out of these things and identify what are these best zones. So before looking at the results, I'll show you this plot again, that this is the current cropping practice where you have a lot of crop of rice in that northwest parts, and the other cereals which used to be the traditional crops are not there currently. Now, when you run this model and identify what are the solutions that come from this model, you'll find that in the northwest part of India, the rice is completely removed and it's been replaced by other cereals, both under the green water scenario and the blue water scenario, which is, assuming there is no irrigation in the entire country, completely green, and assuming there is some sustainable irrigation, which is renewed on an annual basis, that is the blue water scenario. You can see as there's a 75% reduction in how much crop goes into those places, and it's been replaced by traditional crops that used to be grown there. Now, when you look at the national level, how much revenue you can generate, it is much greater, at least 30% greater than the current revenue that you can generate. This is the sustainable irrigation scenario. Even the rain-fed scenario is 5% greater than what you're currently generating. All the other production limits are met, or even we are producing more than what we need for now. This also calls for the story that currently the country imports a lot of oil seeds and pulses, but with this optimized scenario, you can look at reducing those dependencies on external trades also. So the country becomes completely self-sustained for all the types of crops that you need. And an even bigger opportunity here is that if the corporations and government participate together to address market risks and price risks, and also provide help in terms of technology innovations in the agriculture supply chain, the story is even bigger because you're really solving a national problem using a well-established AI technique. In the next story, what I'm going to present is how do we plan United States agriculture for climate change? And I'd like to acknowledge my colleague here from London School of Economics, James Rising. So here the problem was extreme temperatures in the US under climate change will reduce yields for several of the major crops. So the first thing we try to identify here is a learning technique, a Bayesian learning technique to understand and predict crop yields based on technology, temperature, and water stressors. And the solution we proposed are using systems methods to predict crop switching strategies. Very quickly, without taking much time, it has two aspects to it. The first part is a complete yield prediction model that is trying to predict yields for every county over the past 50, 60 years using climate inputs and water stress inputs. Then it's a learning model. So it tries to understand what is the influence of temperature on each of these crop yield parameters. Then the second level is use all these things, all the predicted yields with an economic optimization for decision analytics for future climate. This is akin to the optimization technique. So a quick example of how a yield prediction model looks like. The red color line is the two examples from two counties here. The model predicted yields are presented in the black box plots, the distributions. And the red color line is the observed yield. So you can clearly pick up the technology trend. You can pick up the variability also across the years based on the climate stressors that it's being applied on. And finally, we did the optimization model. We looked at what are the best locations for 2050 and 2070 under future climate scenarios. And you find that corn slowly becomes less concentrated in the Midwest. Soybeans show gradual movement to the north. Winter wheat moves up from the south along the Mississippi. Cotton is grown at higher latitudes compared to now, and it become dominant in the Southern California area. When you look at the overall revenue that the country can generate purely from agriculture from these crops, you can see that the optimized scenarios are always better than the current observed scenarios. Under future climate 2050, 2070 scenarios, you do have reduction in the revenue, but then the optimized scenarios are much better than if you actually continue to grow where you're growing today, because the future climate is going to reduce the yields. That means some locations are not going to be optimal anymore. So we try to find the optimal solutions using decision analytics. Finally, I would like to close with saying that there are multiple possibilities with AI to solve the multi-scale agricultural issues. So the solutions can be applied at multiple scales, and at every scale you have possibilities with AI. Starting with at the national level, if you want to optimize where what is grown, you have analytics type of models to develop those things. Again, at the national level, it's mainly driven by economic signals and storage and management signals. Those also can be, we can use big data to leverage those ideas and try to give better pricing forecasts, better climate forecasts, better market forecasts, so that we adapt to the future conditions. And on the farm technologies, which is like at the local scale, we can have efficiency in irrigation, monitoring and practices. Rain-fed crop productivity can be increased by on-farm technologies. You can have better soil sensing also using all these like robotic technologies and things. For the long term, you can also develop his traditional risk management models, which are rooted in predictive analytics techniques. For that, we can look at food, water, financial storage, development, and trade between various countries, and try to increase the yield of dryland crops using local sources, but also regional solutions across. I'll stop there. Thank you.
I'd like to move on to our final speaker, Aadith Moorthy. He is the founder and CEO of ConserWater Technologies, which uses satellites and AI to measure soil moisture, nutrient levels, and other actionable information about farmland and soils to help farmers grow more with less without using any hardware or soil sampling. Thousands of farmers worldwide currently use ConserWater to save on water and nutrients and increase the fertility of their farms. Aadith is a Stanford Knight Hennessy Scholar and holds a master's degree from Stanford along with 2 bachelor's degrees from Caltech. He has also been named a top founder in AI by TechCrunch. And with that, I'd like to welcome our final speaker. Thank you.
Thank you for the kind introduction. As was mentioned, I'm Aadith Moorthy. I'm the founder and CEO of ConserWater Technologies, where we help farmers worldwide to grow more with less. And I founded ConserWater about 4 years ago, and I kind of want to narrate some of our learnings from doing that and around agricultural AI, where one of the key missions of agricultural AI, at least in my opinion, is to enable farmers to grow more with less, and while doing it in a sustainable manner and at scale. So as you might be familiar with AI from other industries, it's commonly deployed to enable scale to be unlocked. Like for example, when Google or Facebook use AI to target ads, it enables them to scale to billions of people. Why can't that same thing be true in agriculture as well? Can we design solutions that can scale dramatically to hundreds of millions of farmers? Can we design those kinds of solutions? That has been kind of the guiding motivation here, at least behind how we have been approaching this area. And to give you a general idea of how I like to think about AI, at least in its most useful form in agriculture, it's sort of like this picture here. This picture might seem kind of a bit abstract to you, but if you take a second, you'll notice that there's these purple stripes that are going horizontally across the screen. But if you look a bit deeper, if you look behind the stripes, you start to see something is present. And if you were kind of aware of this location where this picture is taken, you might actually recognize that's actually the University of Maine campus in the background. So this is essentially one of the key purposes of AI. At least one of the big potentials of AI in agriculture is that it can unlock these hidden patterns that human beings are not necessarily able to unlock on their own. And then once you've unlocked that, you're able to derive all sorts of value. AI is able to identify these hidden patterns that are very hard for humans to do. Of course, there's also AI that can just essentially replace human beings. But that's not the kind that is most sustainable for humanity in the long term. The best kind of AI, at least in my opinion, is AI that can unlock these insights that you never knew about before, and thus gives you completely original insights that can change your operations, change what you do in a dramatic way. And today, when we think about AI, we usually think about it in terms of machine learning, or sometimes deep learning, which is a subset of machine learning. AI is a very, very broad term. There's many, many different AI techniques. There's expert systems. There's all sorts of techniques that are developed in the past. Then when people generally talk about AI today, they're usually referring to machine learning when people generally talk about AI. And you might be familiar with some of the common methodologies used in machine learning. And I'm going to illustrate in a moment here how all of these can actually find a role in agriculture to do very unique tasks that enable us to unlock all sorts of value. But before I go into that, let me just start out with just a brief overview of each of these types so that everyone is clear on what they mean. So the most common kind of machine learning that you might normally think of is actually supervised learning, the bottom right here. And supervised learning is where you have a set of inputs and a set of outputs, and then you train an AI model, or a machine learning model rather, to be specific, to build a function that goes from the inputs to the outputs. If you gave it the inputs, it can predict the outputs. The computer learns that function that relates the inputs to the outputs. That is supervised learning, when there's inputs and outputs and you're building a mathematical function between them. On the slightly other end of the spectrum, there's unsupervised learning, where instead of having inputs and outputs, you just have inputs. And then you're trying to figure out some relationship between the inputs data without actually knowing any reasonable outputs. It's used to find relationships and between the data, within the data, that is not otherwise visible. And unsupervised learning also has interesting roles to play in agriculture, but commonly you often think mostly about supervised learning and not as much about unsupervised learning. But still, it's useful to have all these frameworks in your mind. And thirdly, there's reinforcement learning. This is what you might think of like Google's Go program, playing the game Go. It became so good at Go through reinforcement learning, where reinforcement learning is a slightly different paradigm of machine learning, where you're trying to understand how to optimize a certain task. How can I optimize to, for example, win a game, for example? And all of these kinds of scenarios find interesting uses in agriculture. So without further ado, when you think about unsupervised learning, this is actually a set of fields from one of our clients actually at ConserWater Technologies. Here you can see that this client has several forms, like dozens of individual fields. However, the reality is that you don't often, when you're on the farm, you don't often have unlimited resources to plow into these unlimited fields. You only have a limited set of resources. How do you allocate those resources in a good manner so that you optimize various conditions on the farm? One way that you can find out actually is by doing unsupervised learning on these fields themselves to find patterns and groupings within these fields, natural groupings, which then to those groupings you can then decide to apply certain interventions. Like, for example, this is just a naive guess from a human eye perspective. AI might pick up further things if you feed it with large amounts of satellite data. For example, here you see that these fields seem to be slightly greener. These fields seem to be slightly redder. These seeds are slightly yellower. Those might be natural ways to break up these fields in order to manage them in a smaller chunks. But there's a variety of things that can be done here depending on what is the final objective for the grower. Is it yield maximization, reduction of disease, whatever is the objective? The unsupervised learning can get you a first stab at understanding what are these various kinds of groupings. But other than that, unsupervised learning is probably still quite in its infancy from its applications in agriculture, because of we just need to find the right problems to apply it to. So without further ado, we come to supervised learning, which is probably, as I mentioned, the most common thing that most people think about when it comes to machine learning. There's two flavors of supervised learning. There's classification problems, where you're simply deciding whether it's a cat or a dog, is what Google's video AI would do. What we are doing here is deciding between various classes in agriculture about what whether something falls into one bucket or another bucket, as I'll show you in a bit. And regression is regression actually quite common in agriculture as well. Much more common, I'd say, than in the general AI in general. When regression, you're trying to predict a quantitative variable, an actual number, as opposed to a class, whether it's A or B. You're trying to predict, is it 0%, 50%, or 100% of some property, whatever property is. So in classification, one of the very, very, very common use cases of AI in agriculture, which has actually gotten quite a reasonable level of adoption actually currently. This is not something that we do at ConserWater, but we find it very interesting to see the levels of adoption that have been reached, is actually in using your phones to take pictures of diseased leaves or diseased plants. And then an AI can simply classify and say, what is the disease? Or with some level of accuracy, it can say what is the disease that's afflicting your plant. You don't need to be an expert in agronomy and understand all of the various diseases that afflict your plant. And as long as this system is trained, the apps that are out there are trained for those particular conditions, they can identify directly. You don't need to call up your agronomist to get this information. It can find this patterns in the leaf directly just by taking pictures. And then once you have that picture, it can identify with some accuracy what are the conditions, and then you can take the appropriate interventions to reduce that the risk that that disease poses to the farming operation. So that's a very, very interesting application. And there have been data sets of various pictures and also disease classifications that have already been collected by various labs around the world, agricultural labs. And using these, people have been able to build deep learning models in this case to directly identify what are the diseases. One other kind of application that we have found actually more directly at ConserWater is by using satellites along with AI, we're able to identify, basically classify on a pixel level where there might be anomalies and potential diseased areas. And what we're able to do beyond that, which is very important in agriculture, is you don't just want to have this analysis, you want to be able to present the analysis in a way that's understandable, easy to use, fast to use for the farmer who might otherwise find it hard to use your technology if you can't actually present it in a useful manner. This is not just true in agriculture, it's probably true in every field. You have to present the results in a manner that are understandable. Here, what we're able to do is we're able to identify on a pixel level where there might be potential diseased areas or unhealthy areas. And then what the next layer of processing on top of that is you go to Google Maps and you place a marker on those areas automatically with code. So then the farmer can then just walk to these markers and see what's going on at that particular area. So what's basically going on here is we're able to use a variety of satellite bands to pinpoint anomalies by using supervised learning with classification to classify pixels and decide whether is this pixel potentially the location of an anomaly, and then direct farmers to those anomalies so that they can manage things more effectively. And then moving on into regression, I think this is already mentioned by Dr. Devineni just before me, is one of the common things about regression, at least today, common use cases actually in crop yield prediction usually on a county level, or it could be sometimes more granular than that. You can do crop yield predictions just based on very basic levels of satellite data. You can get a very good prediction of crop yields, which can then inform not only farmers in that area, but also investors in general when they try to decide whether purchasing corn contracts for this particular year is a good investment decision or not. So all those kinds of efficiency are being unlocked by using satellites and AI, kinds of efficiency that were not present before in the system. But now coming more to where at ConserWater we significantly use supervised learning is in this. By using over 100 satellites throughout the entire electromagnetic spectrum, from UV to radio waves, which is the input data in the supervised learning, if you may, we're able to combine that with the AI models that we train using large amounts of ground truth data in the form of soil tests, for example, actual lab soil tests, or sensor arrays around the world, soil moisture sensor arrays, and convert that, convert what the satellite sees into actionable numbers about plants and soil. Information such as the soil moisture levels, soil nutrient levels, soil carbon levels, a variety of different things can be understood by using a large amount of satellite data coupled with a large amount of ground truth data upon which AI models are trained. And thus we are able to convert what the satellite sees into these actionable numbers. And why that's important is that satellites actually take a huge amount of data, like terabytes of data every single day, several terabytes of data. And overall, like over the course of several years, we have many petabytes of data. It's a huge amount of data. Human mind cannot really comprehend that level of data. And especially the trends shown in the satellite data, it's very hard to comprehend very easily because what the satellite sees is simply raw numbers. It's like your camera on your phone. It just sees the counts of photons that come off of the Earth, and everything else is a derived product on top of that, just the count of photons. And what we're able to do with AI is basically convert those raw numbers into actionable numbers, which the computer system, the AI, the machine learning model trains but trains to understand by looking at the satellite data. So very classic supervised learning, going from inputs to certain outputs that are very relevant for farmers to manage their operations more efficiently. And the best part is that it's actually not like having a soil sensor or a lab test, because we are able to actually use satellite data to get things at an even granular resolution. You could even get like 10 meter, less than 10 meter, even 3 meter. And in customer units, 3 meters would be 10 feet. So even a 10 feet resolution, you can get this information. Using satellites coupled with AI, you can get information at that level of resolution. So all sorts of new things are unlocked, new possibilities. AI is unlocking all sorts of new possibilities as opposed to replacing existing possibilities. And just before we conclude here, a quick note about reinforcement learning. I personally feel reinforcement learning is one of the most important up and coming ways to utilize AI here in agriculture, because it's very important from the adoption standpoint, which was mentioned in the very first talk in our sequence here. So one of the most basic kinds of process optimization leveraging reinforcement learning has already found adoption is actually in indoor farms, because all of the variables are completely controlled in indoor farms, and hence it's a slightly easier problem than outdoor farms when all the variables are controlled. But when you actually go to outdoor farms, there are very, very interesting applications. Like, for example, in this case, we are showing, I guess, some of our partners at ConserWater, for example, Talgil, irrigation controller units. These controller units sit on the farm, and what they're able to do is they're able to use our APIs on the cloud, ConserWater's APIs, to implement AI on the farm and essentially automate the farm. But that's not the interesting part where reinforcement learning comes in. The place where reinforcement learning comes in is once you have a unit like this, we are able to use reinforcement learning to optimize an objective such as maximizing your yield. That might be the most important thing for the farmer. Maximize your yield, or it could be sometimes reduce water use. You want to minimize the water use. There's various objectives depending on the farmer that's interesting for optimization in a reinforcement learning scenario. But once you have this kind of setup, you can then start to think about reinforcement learning in just optimizing the daily decisions, water applied, nutrient applied, using satellites and AI, and crucially on the behavior change perspective, which behavior change is a very, very hard thing to achieve in agriculture. What reinforcement learning can do for you is it can adapt to the farmer's existing practices. It can essentially learn how the farmer manages their farm on a daily basis based on all of these inputs, and then help the farmer to slowly ease them into the efficient scenario provided by the supervised learning models. Like, for example, I'll give you a real example here. We had some farmers who are using 10,000 cubic feet of water per hectare per year is what they were commonly using. And then we had them, what our models were initially suggesting to them is you don't need 10,000, you only need 6,000 when you do all these calculations. But then there's often some pushback because you're going suddenly a 40% decrease. I'm so worried that that's something that's going to happen to my crops. The solution to that is actually to go from 10,000 to 9,900, 9,800, 9,700, slowly ramp it down and slowly ramp it down as per the farmer's existing practices, so that he slowly eases into an optimal scenario where you eventually reach 6,000. You don't drop to 6,000 overnight. This is gradual behavior change, and this is probably the most effective way to achieve behavior change in agriculture. At least that's what we suspect today. By enabling a gradual behavior change, which can also be unlocked by these kinds of AIs, you're able to ease the farmers into new technologies without it being an aggressive change that they're hesitant to adopt. So before I conclude here, I just want to leave you with one last parting thought is all of this is only possible if you have some kind of training data on which you can build machine learning models. So where does this data come from? That's a thought that I want to leave you with here, because that's the most important part as with any AI. You need data to make things happen. There's many creative data sets out there, though. There's many hacky data sets, if you may. Like, you can put together a data set from multiple different sources. You have a very interesting data set that can then unlock new value. But where does data come from? That's a crucial question. And thank you for having me here today, and happy to take any questions if there's any time remaining here.
Thank you, Aadith, and thank you to Naresh and Stephen as well. I think we're getting short on time. So I just wanted to thank each of our speakers for their excellent overview. I think we covered quite a bit of ground between the three of you. I guess one question I might have is, as climate change worsens, would you anticipate that things become more unpredictable? And if so, is there time to respond in something like an agricultural timescale to correct issues, if you will, and to actually, will those predictions become less accurate as the climate worsens?
I guess I could take a quick stab at it, I guess, is, yeah, so the models will get outdated over time. So that is where you have to retrain the models. There's many strategies for that. You could completely retrain the models entirely all the time, like every few years, or it could be a kind of like a online machine learning, as they like to call it, kind of method. If you set up the models that way to begin with, is from using further inputs from the ground, it could automatically be getting better with time. So that's crucial, though. The models have to keep getting updated. You can't, even today, like I wouldn't say it's reasonable to use models developed in the 1980s for doing work today already. So things change, does happen. But sort of the good thing is that climate change is slightly longer timescale event. It's not something that happens like overnight. So the model that we developed today can probably be used definitely for this season, for the next season maybe even, or even for the next season after that. Then, of course, there's probably already better data sources out there. So you're anyway going to retrain the model, but it's very crucial to retrain every several years. You can't use the same thing for 100 years.
Thank you very much. I wish we had more time. The talks were very interesting, and luckily a video recording of this will be available on the UMaine AI webinar website. And with that, I'd like to thank again all of the speakers and also to the attendees for joining us. And as a reminder, the next AI webinar in our series AI and Healthcare is scheduled for Thursday, May 6th from 12 to 1 p.m. Eastern Time. And with that, thank you all for your attendance, and I hope everyone has a good day.